Hi, my name is Nishan Bhattarai. I'm an assistant professor at the Department of Geography and Environmental Sustainability at University of Oklahoma Norman, and I talked about remote sensing of crop water use and using combining remote sensing with other disciplines to answer some of the agriculture water sustainability challenges or questions. Yeah, thanks so much for this opportunity to present my work. So I'm from Norman, Oklahoma. So this is east of Oklahoma City, and at the University of Oklahoma, we are in SEC now, and you know how we are doing, right? So uh, I'm originally from Nepal, and I've bounced around a lot of places in the U.S. And here I am in Norman, Oklahoma now. So by training, I'm trained as a remote sensing scientist as well as hydrologist, and today I'm going to present some of my work on modeling evapotranspiration, which is the water used from crops, or vegetation, right? And using remote sensing, and how we can use those data to answer some of the agricultural water sustainability challenge questions, in the face of climate change as well as the growing uncertainty. The motivation behind the research is that we are going to see a lot of people, like by 2050 the population is going to go almost more than 9.5 billion, right? So to feed over 9.5 billion people in 2050, we need to more than double our crop production, right? So over the last 50 years, we have done pretty well, right? We have actually increased our crop production pretty well to feed the growing population. You heard about this the green revolution, right? So we are able to increase yield, use fertilizers, different varieties of crops and irrigation. So a lot of those things to increase food production, right? And we actually produce more food now than we need actually. So, but then the food are not rightly placed in place where it is needed, right? But we do produce a lot of food. But by 2050, we need to more than double it. And then by 2050, we're going to have the increased temperature as well. So that is going to be decreasing the yield. So we have to face that as well. And the water is going to be scarce, right? So there's going to be less water available. So we already have used so many land, so many water for food production, right? So these resources are finite, very limited. So we have to come up with something to deal with, the warming temperature, which is reducing the yield, and then also deal with the reduced water supply. And the land is going to be same, right? Land resources. So the main challenge here is how do we use water effectively, But then we all know that there's a lot of water in Earth, right? If you count the number, this is 326 million trillion gallons of water. So how many zeros are there? So you figure out, right? So there's a lot of water on Earth, right? So that then you might say that, oh, we have a lot of water. Because when you see the Earth from the space, you will see blue, right? It's water. But the actual water we can use directly, which is fresh water, is only 2.5% of all the water. So almost 72% of the Earth's surface is water, out of which only 2.5% is fresh water. And of those, you can see here, almost 69% is ice and glaciers, right? And 30% is groundwater. And then only 1.2% is the surface water. So the actual amount of water we can directly use is less than 0.5%. And where is this fresh water being used, right? So globally, irrigation is 70% of those fresh water is used for irrigation, for our food, right? In the US, 37% of water is used for irrigation. And in Oklahoma, around 41%. And also in Texas, also there's a lot of the irrigation and water use as well. So irrigation is the main user or source of fresh water, right? It's because irrigated crops are more productive. So out of the total crop production globally, the 80% land are rain-fed agriculture, right? And 20% land is roughly like 80-20, like 76, 80, 20, 76, 24, something. It's very rough number, but there's more rain-fed, agriculture system across the globe than the irrigated agriculture. But the amount of the food produced from the irrigated agriculture is twice than its footprint, right? So it's only 20% of irrigated agriculture, but it accounts for 40% of total food. So it's more productive. So that is why the more area, more cultivated area needs to be irrigated to increase the production to meet that food demand, right? So and then most productive region of the world, so that is where there's a lot of food production is going on, are using water unsustainably, which means they are consuming more water than needed. Right? There's more depletion, and there's less recharge. Right. So, for example, if you look at the region here in the Ogallala aquifer, right? Do you have a clicker or something? No. Do you have a clicker? No. It's fine. So. So if you look at the high plain aquifer, so that is the pink color in this figure shows the water is unsustainably used, right? So which means there's more water consumed than required. Right? So it's and then you also see the California Central Valley, right? Two key irrigated area in the U.S. that produce almost half of the U.S. food, right? So that they are using water very unsustainably. And if you look at other region of the world, like North China plain aquifer, there on the right, and India in Indo-Gangetic plains there, and so those most productive region of the earth, they are using water unsustainably. So one of the way to deal with the water scarcity is using seawater, right? Desalinate the water and use it, and that's being done a lot in the Mediterranean regions, right? Gulf countries. But still, one of the way to deal with the water scarcity is by using the water properly, right? By using the water efficiently. By using the water, by only applying water to the crop, the amount of water that is needed, not more than what is needed, right? So that way we can save the water, right? To use it for future. So to know how much water is needed to be by the crop, we need to know how much water is actually being used by the crop, how much water is needed by the crop, right? So so that's what my research looks at. So in our research, my lab looks at the remote sensing of crop water use or evapotranspiration. So how many of you are familiar with the term evapotranspiration, right? So evapotranspiration is the process by which the water is transported to the atmosphere, right? The liquid water is converted into vapor, and then it goes to the atmosphere. And then evapotranspiration is a combination of evaporation and transpiration. Evaporation is the water lost by the soil, and transpiration is the water used by the plants. So when the plants open the stomata, right, the carbon dioxide goes inside to make the food. At the same time, the water goes out in the process of evapotranspiration. Right? So my research looked at how we can map evapotranspiration, because if you map evapotranspiration, you will know how much water is being used. And if you also map evaporation and transpiration, you also know how much water is lost by the soil and how much water is actually used by the crop, which is transpiration, right? So if you increase the transpiration and reduce the evaporation, that means you are saving water. You are using the water that's needed by the plant, right? And evapotranspiration is also the connecting link between the Earth's energy, climate, and water cycle. Right? So this is the water cycle. You probably have seen this water cycle figure multiple times, right? So evaporation is the process where the water from the Earth, like water vapor, is transported to the atmosphere. In that process, a lot of energy actually goes to the atmosphere, because the water, it takes a lot of energy to the atmosphere, and it condenses, and then energy is released there, and then there's precipitation, right? So that it helps not only recycle the water, but also recycle the energy, and that also regulates the climate. So everyone know like what's the one of the great lake, like Lake Superior, right? It's the largest, one of the largest lake, right? And it has a lot of water. So it has water around 3 quadrillion of water in Lake Superior. That is 3 into 15 zeros, right? So if I tell you that all the plants, like all the plant globally, right, in 1 year evaporates the same amount of water as in the Lake Superior, would you believe me or not? Like all the plant in 1 year takes water almost same as that in Lake Superior and transport it to the atmosphere in the vapor. Would you agree or not? Do you believe? Yes? It actually transports 4 times the water in Lake Superior. So that much amount of water is transported by the plant every year to the atmosphere, and that regulates climate and everything, right? So it is a very important process to understand, and it's also a very complex process to understand as well, because we're trying to estimate something that we cannot see. It's a water vapor, right? So my research looked at how we understand how we use remote sensing to understand the crop climate and human systems interactions, and how is ET linked with the crop climate and human, right? So so we know that the crop needs water to grow, right? So that's the main thing that crop needs to grow, right? To make food, to transpire, and that water is supplied either through precipitation, like rainfall, and if the rainfall is not enough, then irrigation has to be applied, right? So that's why where the human components is there. So there's a very direct link between how the crop or agriculture, climate, and human system are linked through water, and then water. When there's water, there's ET as well, right? So there's a very direct link, but the process is actually very complex. It's because a lot of things are changing here, right? They are interacting with each other. For example, we humans are the main contributor of, the warmings, right? Climate change, right? And then with climate, it affects the crop production as well. Like warming temperature would reduce yield, right? And we also change the cropping patterns, and it will change the crop production, water use. So there is a lot of like dynamics within the crop climate and human systems, and ET or water is the connecting link, So ET is actually the vegetation or crop response to the environmental changes, right? So vegetation is actually you can say vegetation as a sensor itself. It's because whatever is happening around in environmental changes, the plant is responding silently, right? It's responding, and if we understand how plant is responding to changes in environment or climate, we can actually relate how the climate is changing by looking at this response of vegetation. In remote sensing, we have taken a lot of images. Like we take millions and millions of images every day, like through remote sensing, different sensors. There are thousands of sensors out there, satellites and UAVs, and so there's a lot of images, and we're doing that over almost more than 50 years now, right? So if you look at all those images, and if you look at how the vegetation or crop responded, over time, then we can actually look at how was the climate at the time or something. So that can be linked, over time. So so that's how remote sensing is used, right? But then So over the last like 50 years, remote sensing has been very useful in understanding a lot of processes, like how the land cover is changing, right? How the plant are responding to different changes, or how yields are changing, or a lot of things that we have mapped over time, right? But when things are linked with human systems, it's very difficult to like map that. For example, how would a farmer respond to irrigation? Like how much water is applied to the plant or something? When there's a human component attached, then it is really difficult to map that, right? So how do we map when I make some changes? I thought something and made some changes. How that can be mapped? So it's very difficult. That's why remote sensing is combined with other disciplines to understand those human interactions, right? Human climate and crop interactions. So it's a more interdisciplinary approach is needed, which can help connect pixels to people, right? So interdisciplinary approach is an approach that combines like tools, methods, techniques, data, from different disciplines, right? And in my research, we mostly look at the hydrological and hydrology and eco-hydrology and remote sensing, right? So my lab at University of Oklahoma is the agro-eco-hydrological remote sensing lab, and we do a lot of things. We map ET, right? And we also map yield as well. So this is a yield map of India. So that is from my PhD student, who is actually deriving those map from rice and wheat, over all of India, right? And this is another figure right here. This is mapping evaporation, evapotranspiration, and ET, all three components of ET, all two components of ET, and the combined ET. From a vineyards in California, right? So we're working with the USDA and a wine company, really hard, that EJ Gallo wine. I think it's called Gallo now. It changed the name, but then so these are the vineyards owned by the Gallo company, right? And also looking at how the groundwater depletion will look like in future in India. So things like that. So we combine remote sensing with eco-hydrological modeling, statistics, and then with several other tools to understand the agricultural sustainability, water security, and global sustainability challenges, right? So over the next few slides, I'm going to go over like two key things. Like this is going to be my outline of my talk. First, I will talk about this the method that is used in modeling ET or remote sensing of ET, right? And then in the second part, I will talk about how this ET and these remote sensing products are used to understand the crop climate and human interactions. So the method development in remote sensing. So how do we map the water that we cannot see? How do we map the water that is used by plant, right? So there are different processes. There are also different methods. The method that one of the most widely used method is looking at the surface energy balance, right? In the surface energy balance, the main source of energy on Earth is sun, right? Solar energy. Right? When that energy is received by all the surface, that energy is used in different ways, right? Some of the energy, like for example, this plant, here the RN is the net surface radiation. So that radiation is the amount of energy that is retained in the system, right? So some of the energy, solar energy, comes, here's the plants, and it's reflected. Some of them are reflected, and some of them are left in the system for different processes, right? So RN is the net surface radiation. So that is the total energy that is available, and some of the energy is used to heat the soil. So Z is the soil heat flux. Some of the energy, because when there is a change in temperature, that means there is also change the heat transfer of the energy or heat, right? So then again, the first law of thermodynamics, right? The water, the energy is neither created or destroyed. It's just changed from one form to another form, right? So some of the net radiation is used to heat the soil. So the soil is heated. Some of them are used to heat the air, right? That is sensible heat flux. The soil heat flux is the one that goes to the soil. Sensible heat flux is the one that heats the air. It's called sensible heat flux because we can sense it, right? So if you touch some hot object, you will feel like very hot, right? Because it has high sensible heat. So some of the energy is used for that, right? And the other energy is used for the process of ET. So that is latent heat flux. So it's called latent because it's latent. It's not seen. It's not felt. You cannot feel it, right? That's why it's called latent. And latent heat flux is the one that is energy is the one energy that is used for a process of evapotranspiration. Here the lambda ET. So lambda is the latent heat of vaporization. So it is the amount of energy that is used to convert 1 unit of liquid water to water vapor, right? And if you multiply that by total ET, then you can get the latent heat flux. In the ET modeling, the net radiation is computed, right? Soil heat flux is computed, sensible heat flux is computed, and then the remaining part is the ET. So either you the total available energy is net radiation minus G, that is the available energy, and you can separate that into sensible heat flux and soil heat flux, right? So sensible heat flux and latent heat flux, and from latent heat flux you can get ET. So that's how it's done, right? So so there are different my lab had looked at different challenges on remote sensing of ET. For example, some of the methods are not fully automated, so we develop codes to fully automate the process of evapotranspiration. Deal with the cloud availability. And in some region there's not much data available, so we deal with that as well. And also run different models and try to create a ensemble model of ET. And also evaluate different model across different vegetation cover types. So what we have found is, so there are different models developed to map ET, but there is no agreement on which model is best, right? If you look at the ET product out there, you will find tons of products, right? But there's no clear agreement on that this product is the best product. So whoever develops the product will say that, okay, my product is the best product, right? Because I developed it, right? So because you, but then when you independently evaluate this product over different regions, what is found is there's not a single model that works best under all conditions. So these are some of the models. So you see this, the SSCBI, CVAL, metric. So those are different ET models, right? They compute this latent heat flux differently, right? So that's why there are different models. And what we have found is most of the model doesn't work very well under dry conditions, right? When we need it the most, right? And the dry condition, we want to estimate the water use more accurately, right? Because we need to apply, we want to apply the accurate amount of water, and save water, right? And the dry conditions, the model are not perfectly working, right? They are under wet conditions. The SM is the soil moisture there. So, soil moisture was less than 10 percentile. The model errors were higher, right? And then, so we develop a new ET model, which look at the, it's called STIC. So this is a very complicated figure of how the ET modeling is done. So what I'm doing here is, if you look at the red font here, the one in the red font, right? TR, which is the surface temperature, albedo, emissivity, right? NDVI, like normalized difference vegetation index. So those are coming from remote sensing. So that is coming from remote sensing, right? So what the model does is it uses this remote sensing products, combines with the meteorological climate data, right? And then solve the process of the surface energy balance process and compute the latent heat flux. This is one model that we had developed. I work with the model developer STIC, and then the model was initially only developed for point scale, at a point scale. So we worked together and developed a remote sensing version of the model. And This is one of the models that the NASA is actually going to be using and developing ET product very soon using eco-stress sensors. So we found this model actually work better than another model called SAVES and then MODIS product. So MODIS ET is the NASA ET product. So what we found was when we applied over the US, under dry, normal, and wet conditions, the model actually worked better than the other two models, including the one from the NASA product. But then when you look at the irrigated site in Nebraska, which is called maize site in Nebraska, the model actually didn't work better. It didn't work better than it's not as good as another model called SAVES model, right? So again, now come back to the same point. Like you can develop model, you can change the model, but you cannot make a perfect model, right? There's always going to be some limitation of model. So in this case, what we found was under very heavily irrigated conditions, the model is underestimating ET, right? So that was another challenge. So because there are different models that develop, right? So what we thought is maybe we can combine different models. When you combine different models, maybe you can come up with some model that works better than the individual model, right? So when you combine different models, maybe the good part of the model is taken and some of the uncertainties are removed. So that's why we actually run different models in India. So this is one of the project that was funded by NASA. So we develop a ET product for all of India, right? And so India, there's a lot of irrigation in India, especially in the Indo-Gangetic plain, right? And there's a lot of agricultural land in India. So India is one of the main agriculture country. And so we use a lot of data here. We use almost every MODIS daily and 8-day data, and a lot of the NASA, the reanalysis data, and run different models and fill the cloud and develop this 1 kilometer ET product for all of India. And then what we found was here, if you go to the last one, the OnSave, that is the ensemble ET. What it does is it takes the mean ET from all models, right? What we found was the mean value from all different models is actually better than the individual model. So we'll combine all the models, we are getting a better results, right? So it complicates the things because we have to run more models, right? And more computational power is needed, but then you're getting better results, right? So that way we're able to deal with some of this model uncertainty, right? And then so this is in India, so there was not many observed data available. So we were only able to get few data, and then we found that the ensemble of different models work better than the individual models. And these are the map. So the left one is the map of ET, and the map from the ensemble model. This is a mean 16-year ET, and on the right side are the ET maps for the same time period, the mean ET from different global ET products, right? So you can see the green stripe there, right there on the top there. So that is the Indo-Gangetic plain. That is the region where there's a lot of irrigation. So that region is the bread and basket of India. Right? I'm talking about the one in the green, right? The green stripe like this, right? So that is the Indo-Gangetic plain. So there's a lot of wheat and rice, production and irrigation there. When there's more irrigation, there's more water use and more ET, right? So that is not well captured in some of those global ET products. If you look at the MPI, GLDAS, even MODE 16, so that is the official MODIS product, ET product from NASA. So they are not very capturing well that high ET from those regions, So the ensemble ET that we developed was able to capture that. So in the ensemble ET modeling, what we do is we just take the mean value from different models, right? So that means you are giving equal weight to different all models, right? So if you take a stat class, you would just take a arithmetic mean of those. That means you are giving equal weight, right? But what we also know is these models perform differently under different conditions, right? Some of the model may work well under like high biomass, or if there's a precipitation in the last few days, the soil moisture is high, maybe one model is working better, right? So what we thought, maybe we can use some machine learning algorithm to train the model and find that which model worked best under conditions, and then give different weights to different models based on the actual conditions, actual environmental conditions, like high and low biomass, different growth stages, dry, wet conditions, right? Of course, we cannot do this in India because our data is very limited, right? If you look at here, these are the only few points, right? And you cannot run a machine learning algorithm in few points, right? So you need thousands and thousands of points, right? So that's why what we did was we looked at the global. These are the flux towers. So flux tower these are eddy covariance flux tower where ET is measured, and this is global agriculture sites, and the data is freely available daily, and it's a lot of data. So we were able to get 109,000 observations, right? And then now we train the model using machine learning. Again, the goal is to identify which model works under different conditions, and then based on that, give weight to different models. So what we found was, so these are different. So if you look at the right under there, the first one is the mean. So mean of all models, right? So so that is the root mean square is 24, which is 24 watt per meter square. So that is the latent heat flux, and from and other are different machine learning algorithms like the Bayesian, average, mean average, KNN, the K-mean nearest neighbor, and SVM is support vector machine, RF is random forest, and MLP is the multi-layer perceptron ANN model, right? So these are different machine learning models that was trained using those data, and try to give different weights to different models based on different conditions, and they do more like a weighted average, right? So we found that the machine learning algorithm was able to capture that model performance under different conditions. So it worked better than mean. Just taking mean, you can see RMSE of 24 there, 24 watt per meter square. Then if you look at the MLP, this is 19 watt per meter square. So you reduce that error, right? When you reduce the RMSE, then your performance is increased, right? Better, right? So machine learning was able to capture that. The algorithm was able to capture that, right? And also we are also using the deep learning algorithms again. So, but we don't find the deep learning to be as effective. Deep learning is also machine learning, but then not as effective as the support vector machine. So this is it's called like convolutional neural network, and this is a one dimensional because we are looking at the point scale, right? So we don't find it very, but we find it's like slightly better than the other models, but much better than the mean models. So using machine learning is more effective to capture that model performances. And we're doing a lot of ET mapping in California, right? So these are some of the vineyard. There's flux towers in those vineyards. It's a joint project between USDA and the EJ Gallo wine company, and it's also funded by NASA. So so we're actually deriving these ET maps over in California across all the vineyards, right? And there's actually a lot of vineyards in Texas as well. So we could probably do that as well. And what we find was when you combine like multiple like sensors like Landsat and Sentinel-2. So Landsat is the official satellite of NASA, and it's combined actually NASA and USGS, right? So Landsat. So Landsat is the most successful remote sensing satellite mission globally. There's no one even close, right? Because Landsat was first launched in 1972, so it's more than 50 years now. And so we use the Landsat data, and then we also use the Sentinel-2. Sentinel-2 data is the data from the satellite from the European Space Agency, ESA, right? It has very similar bands at Landsat 8. So when you combine those sensors, two sensors, we'd actually capture more better temporal resolution, and then we capture those changes in ET over time. Because ET is very dynamic process. If something changes, ET will actually change very fast. It's very highly dynamic. And if you don't have image, so Landsat 8, temporal resolution is every 16 days. So every 16 days you will get one image, right? And if there's a cloud, gone. You have to wait another 16 days, right? And Sentinel-2 is have 5 days of temporal resolution. So every 5 days you get an image. Sentinel-2 has 2A and 2V, which means it has two identical sensors. So one satellite goes from it's called like ascending mode, which is from south to the north. Another one is descending mode, north to the south. When there's two identical sensors like on the near polar orbits, and then you are actually increasing the temporal resolution by two times. So each sensor will take 10 days to revisit us, right? And when you combine two sensors, you get image every 5 days. So when you combine that 5 days Sentinel-2 and Landsat, you get image every few days, right? So when you do that, you capture the temporal variation in ET better than the single sensor. So that we found in California. We're also doing the winter wheat water monitoring in Oklahoma. So which state is the number one state in wheat production? Can anyone guess? Number one wheat producing state in US. Kansas, yes. Kansas is number one, yes. Yeah. No, not. So Oklahoma ranks 6, right? Oklahoma is 6th wheat production state, and Texas is also there, right? Ahead of Oklahoma, because it's big, right? Much bigger than Oklahoma, but still, Kansas is always number one, right? In wheat production, but Oklahoma used to be not too long ago. Oklahoma used to be second, right? It used to rank as a second wheat producing state, and even in 2012, right? But it's now 6th. Because the crop have switched other crops and there's other things, and then in the recent years, especially in the last year 21 to 23, the El Nino, the fact there's a lot of drought, and the wheat production was declined a lot, and so we're trying to map the water use from winter wheat in Oklahoma and actually in Texas as well. So these are where winter wheat are farmed in winter wheat farms in Oklahoma, and there's that site is one of the site is the USDS site where there's a flux towers, and we are measuring the water use from wheat, and we are changing. There's a like a wheat under different conditions like graze, non-graze, till, no till, different conditions. We are actually and the mapping ET and then modeling, absorbing ET using towers, flux towers. And then using remote sensing to validate that, right? So one of the first thing when you start like mapping ET is, try to save time, right? We try to see like whether there is available data or not. Maybe we can use it, right? If there's someone has already done that, then there's no need to like repeat or make that work redundant, right? You want to do a work that is more complementary than redundant, right? For that, we actually look at the what are the available products, and can you use it or not. So if you look at the errors there, it's actually pretty high errors, So percent bias of in some cases 274%, 13%, 30%. So that is very high errors, right? If the ET it is higher, then you are not absorbing ET like more effectively and more accurately, like reliably. So existing product doesn't seem to be work, Even the Open ET product. So have you heard about Open ET? So this is a NASA funded project, a big project that is mapping ET across all the western US, including Oklahoma and Texas. And this is also a product actually being used by Texas Water Development Board. They're using it, And so we find that the model is actually not very effective, especially in those winter wheat farm sites. So what we're doing is we're mapping on our own. So we have a funded project from USGS where we're actually mapping winter wheat ET across not just winter wheat, but also other crops as well. So this is the winter wheat farms, those sites there, and also in Texas as well. And we're using Google Earth Engine. If you're familiar with that, the Google Earth Engine is a cloud-based image processing tool from Google. It's free for us, for academia. It's free. They have also the commercial version as well. But with Google Earth Engine, you can process a lot of data, and you don't have to download any data, right? So it's actually it's very powerful tool, right? Because we don't have to download anything. You can just process in the cloud and use the petabytes memory of of Google, right? So we are mapping evapotranspiration, which is E plus T, evaporation and transpiration, right? And also individual component of the ET, right? Transpiration and evaporation. So we're doing that, and over actually all of Oklahoma, and as well as we're doing that in Texas as well. So I don't have results for Texas because it's very early stage now. So we have just started the project this fall. So now I'm going to talk about how we use ET and remote sensing data to understand the crop climate human interaction. So the earlier there was more like a model development, technical, like the component, right? So now more interdisciplinary work, right? So for that example, I want to present is from the work that we have done in India. So India is the second largest product producer of wheat, right? And also wheat and rice, and they use a lot of groundwater. So India is the number one groundwater user globally, right? And number 2 and number 3 are US and China. But the amount of groundwater that India uses is more than amount of water combinedly used by US and China. So number 2 and number 3, even if you add the water used by US and China, you will still be using less groundwater than what India is using. So there's a lot of groundwater used in India, right? And so these are the regions where the groundwater is falling down. So those regions in the northwest region of India, that's the bread basket of India, that's using a lot of irrigation for rice and wheat, And then temperature is warming, right? So it's going more hotter, and when temperature warms, the atmosphere demands more water, right? When atmosphere demands more water, that means you have to apply. The ET will try to increase, right? When your ET increases, that means you also need to apply more water. So things are getting more challenging in India, right? So we looked at, when we looked at a scenario when what happens when the temperature increases, and how it will affect the groundwater depletion and India, because when the temperature increases, the demand for water increases, right? So, and you have to apply more water to the crop. For that, you have to irrigate more water, and when you do that, you are actually depleting the groundwater, right? In the long term, actually, you are actually using more water to irrigate, and with that, you are depleting, right? The groundwater level will go down. So we looked at that. We asked 2 questions like, what are the impact of warming temperatures and groundwater depletion on crop water stress? So we are trying to use more water to reduce the water stress. When you reduce the crop water stress, you likely increase the yield, right? Because if the crop are water stressed, then they will not produce, the yield will decline, right? And then we asked like, what is the impact of warming temperature on groundwater depletion in India? So we used a lot of data in India. So one of the data was the groundwater level data, right? So measurement data. So these are those points are the points where the groundwater level are measured, right? And so in India, groundwater is balanced by recharge in monsoon season, so which is like June, July, August, September. So there's a lot of rainfall in monsoon season, and the groundwater level will go up in the winters, and then in the winter season, the dry season, right? And it's like when there's irrigation, the groundwater level will go down, right? But there's also irrigation in monsoon as well, like rice and other things. But then, if the withdrawal increases, then there will be depletion. If the withdrawal is more than recharge, then there's depletion, right? And we look at we use the panel fixed spec regression model. So in the regression model, what we look at is what is the effect of increased temperature on crop water stress, or what is the effect of groundwater depletion on crop water stress, or what is the effect of warming temperature on the groundwater depletion, like that. So we use regression models. This is a panel regression model, also it's also called panel fixed effect regression models. So I have slides. If you want to go detail into that, I have extra slides, but I'm just going to present the results for the sake of time. So here you can see this. This is the results from the regression models. So on the x-axis, is the cause, right, and the y-axis is the effect. So here in the x-axis you can see like what happens when the 1 degree, there's a 1 degree increase in temperature, right? What happens to the ET, change in ET by PET. So ET is the actual ET, PET is the potential ET. So PET is the demand, right? When ET is equal to potential ET, that means the demand is met. So if it is 100 or 1, in terms of percentage, if it's 100 or it's 1, that means all the water demand was met, the plant are not stressed, right? If the value goes down, that means plant are more stressed. So you can see this negative, if it's negative below 0, then that is plant are more stressed, right? So if the precipitation increases, plant are less stressed. So that's why it's above the 0 line, right? But then that effect, we don't find that effect to be much higher actually, because 1 degree change is a lot. 1 degree change is considered a lot of change, because typically in 1 year, the increased temperature is maybe like 0.1 degree, something like that. So it's not much, right? But if the 1 degree increase, there's and then on the last one is 1 meter decline in groundwater. So 1 meter decline in groundwater, there's not much change in water stress. So even though the groundwater is declining in India, the farmers are still able to irrigate. It's because in India, groundwater is like ungoverned, right? And it's subsidized, right? In some states, it's even free to use electricity to withdraw water, right? So to pump the water. So highly subsidized, highly unmanaged, right? And it's a lot of cases it's very free. So they are using the withdrawing water at their will, right? When there's increased temperature, more demand, they're using more water, even though water is declining. And then in the second figure, on the bottom figure here, so when there's an increase in temperature, the change in groundwater. So change in groundwater here means the recharge plus withdrawal, right? If it is negative, that means it's declining. So when the water temperature is increasing, the groundwater level is actually decreasing. It's because there's more water needed to irrigate the crop, right? And when you map that, so that is the second figure is under different RCP scenarios, different climate change, different scenarios, right? When there's so 8 RCP, like there's 6.0, like even there's also 8.5. So those are like more extreme scenarios, right? The mild level scenario is 2.5, right? So when there's more extreme scenarios, it's increasing. The temperature is increasing, and there's more depletion of groundwater under different. If you combine all of them, the groundwater is actually for one is almost from 2050 to 2070. What we found was groundwater depletion may even like triple the current rate in India because of those increased demand. And if you look at the figure on the right side there, so the groundwater is declining mostly in the northwest region, right? But that will expand to other regions like south, even central India. So in future, with warming temperature, those regions will also face the groundwater depletion as well. And that groundwater depletion will negatively affect the crop production. So this is also coming from regression models. So here, if it is below 0, then it's a negative effect, right? So with increasing temperature, with increasing groundwater decline, the different crops, their yield or production will decline, right? And also the intensity of crop production in India will also decline with with groundwater depletion. So the groundwater depletion will eventually negatively affect the crop production in India. So that was the overall research that kind of research that we do in our lab. And what we find was we find that remote sensing is a very effective tool to map ET crop water use, and you can map like water use over a large area, right? Because remote sensing gives you a synoptic view of like a bird's eye view of like large area, right? So you can use the same algorithm, but you can get the like information from a lot of points and regions, right, at the same time, compared to if you go to the field observed, you will just get a value for one point, right? With remote sensing, you can map everything, right? And there are different remote sensing products, so there are, and also different models. So there are a lot of opportunity to to map ET and water use, using remote sensing, and so. But there are still a lot of uncertainty, I know we work on developing different models, then we also find there is still some uncertainty, So there are people working on ET, over decades. I know people. I have supervisor working on ET for almost 4 decades. Still there's the more you work on, the more uncertainty you will find, right? So when I was doing my master's at Auburn University a long time ago, I was very confident at the time. I was like, okay, I'm going to map ET. I told my professor that I'm going to map ET very accurately and give you the ET map. Right? I was more confident then than now. Because when you work on this over time, now you will see that what uncertainty are in those models and the approaches that you use, and also in data as well, right? So there's always going to be challenges. The best thing is to work with the challenges and try to like derive products that are more usable, like actionable, right? So for example, we can map ET over time and look at changes and study like how the irrigation pattern is changing, how the crop is responding, how the farmer's decisions are changing, things like that. So we can use, even given those uncertainty, we can use those products and use it in a way that we can answer some of the critical like sustainability or water sustainability questions. So that's how we can figure out. We can. So so that is important too. Kind of like you work under those uncertainty. And especially when remote sensing products are combined with field and climate data, there are a lot of useful information that we can derive. And interdisciplinary approach is the way, is the approach to better understand the crop climate, human water systems dynamics. It's because these systems are highly interlinked. And because when you combine information and tools, techniques, approach from different disciplines, you are able to there is better chances of capturing those interactions, than using a single discipline, right? So there's the collaboration, and then it's very important here, right? The interdisciplinary work is very important, So that's it, and I want to thank a lot of people, and also fund my students as well as the funding agencies, And also thank you all for listening, being such a nice listener, and I really appreciate the invitation for giving me the chance to present my work, and I'm really happy to take any questions, suggestions, or anything. Thank you so much.